All right, I don't know what happened to the actually the recording. It, appeared the message and then it shut down. All right, so anyway, so let me continue with this. So here actually I want to look at R prime. Let me look at R prime, and this is A Q prime B, and then I'm gonna subtract actually a smaller number, which is the Q plus 1. So I'm going to replace in here, so I come up with this is less than A because, I'm subtracting in here actually a smaller number. And which make it actually a bigger one. Well, I want to rearrange this, so I can write this one as A minus QB, okay, by multiplying the B inside, and then this is minus B, like this. But the A minus QB, this is equal R minus B, and remember B is a positive number, so this make this quantity actually less than R, okay? Sorry, less than 0. Because remember in here, one more time, we have the R, actually is in here, the R is less than B, so when you take R minus B, you get less than 0. So this is less than 0. Well, we have a contradiction in here because this implies that R prime is negative, so this is a contradiction. All right. Similarly, we can actually prove if Q is bigger than Q prime, just actually switch things around in here. Then you come up with a contradiction. So what does this mean? This means I cannot have this assumption that Q does not equal Q prime is invalid, is incorrect. So we must have these equal to each other. All right. So this proof is the Q, the portion must be unique. So therefore, we have the Q is equal to Q prime. Well, let's put this in here. So we have the A. All right. In one hand, we have the QB plus R, and on the other we have, since the Q prime is the same, so it's going to be again QB plus R prime. All right, now equating these to each other, then we have BQ, we could cancel this out, and this leads to R must equal R prime. So this completes actually the uniqueness of Q and R. All right? Let's move on to consider this restriction that we put in B. Remember that we require B to be non-negative. Actually, it must be positive. I'm sorry. We want B to be positive. We know that we can divide, because kind of remember that the division algorithm is the process of dividing an integer by another integer. We can divide by negative numbers. The only thing I cannot divide by is 0. All right? So we had this remark that the restriction on B to be positive is not necessary. In this case, in the case B is any non-zero real number, non-zero integer means positive, negative, and so on, we have the following lemma, the following corollary. The following corollary. Okay, here it is. Let A and B be any, be integers, such that B does not equal to 0. Then there exists unique integers Q and R such that A is equal to QB plus R, where R is bigger than or equal to 0, but less than the absolute value of B. So we're going to replace the B by the absolute value of B. Of course, for the case when B is positive, we end up with actually the division algorithm itself, but when B is negative, then we need the remainder to be positive. Okay? All right, to prove this is actually we're going to apply the division algorithm to the absolute value of X. Sorry, the absolute value, what I mean, of B. So the proof of this we apply the division algorithm to A and the absolute value of B, which becomes Z. So in this case, we have the following. There exists, okay, because this is a Q prime, okay, then times the absolute value of B plus R, where R satisfies this condition. Well, in the theorem or in the corollary, we have the way we express A is in terms of Q, B, and R. So the R is fine, the only thing we have the absolute value. So we need to look at, well, what happens when the case is actually we have the absolute value. So if B is positive, then there is no problem. We have A is equal to Q prime B. The absolute value of B is the same as B. So if this is the case, then this is equal to B. And this gives us this, right? So we simply, in this case, just left the Q equal to Q prime. So we get the 4 we have. On the other hand, if B is negative, it cannot be 0, remember, then the absolute value of B is negative B. And this equation is going to be A equal to Q prime times negative B plus R. Now I can, in this case, we're going to let the Q equal negative Q prime. So then I can write this in the ordinary way. UB plus R, and in both cases, of course, R is bigger than or equal to 0, less than absolute value of B. All right? So there is no change in the R. It must be between 0, including 0 and absolute value. All right. Our next objective is to look at some of the applications, some simple application at this stage of the division algorithm. We know that integers can be characterized in a variety of ways. One way is even odd, okay? Now, actually this characterization of integers to even odd is one among many other types, similar kind of characterization of the integers. And the division algorithm actually supplies the reasoning why it is the case. All right? So here is some examples or some applications of the division algorithm. Every integer A is either of the form (2k) or 2k plus 1 for some k in Z, where Z is the set of all integers, positive, negative, and 0. To prove this is actually all I have to do is to apply the division algorithm to A being any and B becoming equal to 2. All right? Then according to the division algorithm, what we have here, A is equal Q, 2Q, it's better to write it this way, plus R, where R is between 0 and the Q is 2. The B is 2. Well, the only values for R here are these, R equals 0 or R equals 1. And so this implies that A is going to equal 2Q or A equal 2Q plus 1. Where the Q, remember that the Q here, it is any, actually is any integer. So the R is this and the Q is in Z. It's not, I don't know. Well, we call this one K or a Q, that make any difference. Actually, we could put it in here as a K. All right, let's look at another one. Along the same line, we know that every integer can be either of the form. You can choose whatever you like. Let's say 3K or a Q, let me use this, 3Q plus 1 or 3Q plus 2. Now, to get to these different forms, multiple of 3, multiple of 3 plus 1, all right, and multiple of 3 plus 2. Or sometimes we characterize these are the integers which leave 0 remainder when divided by 3. This leaves 1 a remainder, and this leaves 2 remainder. That's the A. Okay, with these different forms. And in this case, all we have to do is to apply the division algorithm to A and the 3. Okay? And then you give you that form. All right, let's look at another example. Let's assume that we take squares of numbers, and we would like to look at the different forms a square has. All right, so in this example, I want to show that the square of an integer is either of the form 4k or 4k plus 1. All right. Another way of saying this, all right, so this is equivalent to saying that the remainder of dividing n squared, that's the square of an integer, so n is in g, is either 0 or 1. Okay? All right, let's see what's going on with this. So in this case, we're going to use the classification of the integers into, so an integer A is going to be of the form 4k or 4k plus 1 or 4k plus 2 or 4k plus 3. So any integer can be written in this form where k is an integer. Now if you square this, you end up with 16k squared, and you can write this as 4 times 4k squared, which is 4k prime. So it has this form. How about if the integer that we pick and we want to square it, has this form. So in here we have a squared is equal to 4k plus 1 squared, and it's equal to 16k squared plus 8k plus 1. And once again, you can write this one as 4. Of course, you can write it in a different form, but say for sure it is of the form 4k squared plus 2k plus 1. And which is again, we can write as 4k prime or a different k prime like this. So it has this form. When it is like this, and see what it produces, which kind. It is 4k plus 2 squared is equal to, again, 16k squared plus 16k plus 4 plus 1. This time, again, I can factor a 4 from the first 3 terms. Plus 4k plus 1 plus 1. Once again, it is of the form 4k prime plus 1. And similarly, you do this one, you calculate this, and you will find it has actually the form 4k plus 1 again. So this one, it's going to be of the form 4k prime plus 1 as well. All right. Let me move on to so again, we could write saying this one that if the square of an integer must leave a remainder of, again, 0 or 1. It doesn't leave a remainder of 2 or 3. That's another way of saying actually this statement. All right, let me move on to define the binary relation on the set of integers called divide. Okay. Here is the definition. Well, an integer B is said to be divisible by an integer A in simples we express this, or we use the notation to express this. And this is the notation, which we say that A, and then we put B in here, okay? And we read this, actually, A divides B, all right? In other words, we use two words in here. We say B is divisible by an integer A, or we use this notation and we call this is actually A divides B. If and only if B is equal AC for some integer C. But in order for this to make sense, really what we are doing in here, we are dividing sort of B by A, okay? So in other words, when we're saying in here B divides A means A, all right, we are dividing, sorry, we are saying that B divides, all right, A means B over A is an integer, right? Well, in order for this actually to make any sense, we require that the A is not equal to 0. So we need to maybe make this one here to by a non-zero integer. So let me add this in here, all right, by a non-zero integer. Integer A, all right? And from here on, whenever we use this this word, we always assume that A is not equal to 0. So again, simply saying that we have this relation, all right, that between two integers, which we say it is divide, then we have A divides B, if and only if B is equal AC for some C in Z. All right. So for A, B being integers, A does not equal to 0. We have this relation defined this fashion. All right? Of course, it's very simple to come up with some divisibility. For example, 4 divides 12. All right? Since you can write 12 as 4 times 3. All right? Similarly, you can also take some negative 24. All right, since negative 24 is equal 8 times negative 3. So we allow positive, negative, and so on. On the other hand, 6 does not divide 8. All right, because you cannot express 8 as a multiple of 6. All right, and this is what we say when the relation is not satisfied. In fact, there are several ways we can express this relationship between 2 integers. One of them is called divisible. Okay, divides. That's another term we use. So we use this quite a bit. It's divide for this vertical. And A, vertical B, it means B over A. Okay, so this, it has to go to the opposite. It's not a slash that with an angle. So this one is B over A is an integer. Or sometimes we say that it divides evenly. All right? Other names we use is we write it down in here, the different way of saying this relation divide. So we have A, so the way we read this one, A divides B, that's 1. Also, we say that B is a multiple of A. Or we say also A is a factor of B, because this means B is equal some A times something. So it's either a multiple, B is a multiple, or we say it's a factor. All right, because in here B is equal A times something. All right. One other name we call, in this case, let me see which other name in here. A is a divisor. A is a divisor of B. The word divisor means it divides, okay? Or it's a divisor. B, when you divide it by A, you come up with an integer value. All right. Now, also another fact, just a quickie fact, that if A divides B, then, of course, negative A divides B. So when we want to look at the divisors of some number, we might restrict ourselves actually to positive divisors. So when we talk about divisors, we might restrict ourselves because it follows from, regardless of A being positive or negative, if it divides, then the negative of that is going to divide, all right? And this is, of course, true because this means B is equal AC, and in here, B is equal negative A times negative C, all right? It gives you the same thing, right? All right. I want to list some properties of this relation divides, and these are very straightforward actually to prove. I'm not going to prove the whole thing, but I will, just as a sample, I'll prove some of these properties. And probably I might stop after this. It looks like we need another lecture on the greatest common divisor. All right, this is actually stated as theorem 2.2 in the textbook. Okay. So in here, again, whenever we use this relation divisor, remember that we require that the A, when we say A divides B, we require A to be not 0. So we don't have to state this, okay? So it is to be understood implicitly that whenever we have a divides relation, means it makes sense. We are not dividing by 0, basically, okay? So that A, B, C, these are integers, then well, it's a big list. So first one, we have A divides 0, 1 divides A, and A divides A. All right. So all of these actually work for any. In this case, of course, we need A not to equal to 0, and in the last case, we don't want A equal to 0. Second property is A divides 1 if and only if A is equal plus or minus 1. All right. And 3. We have if A divides B and C divides D. So we might have another even here, maybe A, B, C, D, all right? Then I can sort of multiply, then A, C divides B, D. Number 4 is if A divides B and B divides C, then A divides C. Number 5, A divides B, F. Let me put an F in here. A divides B and B divides A. But actually not. This is an if and only if. Okay, so this one, if and only if. A equal plus minus B. All right? Or another way of saying this, the absolute value of A is equal to absolute value of B. All right? Number 6, if A divides B and B does not equal to 0, then the absolute value of A is less than or equal to absolute value of B. And 2 more, 7, if A divides B and A divides C, then A divides A BX plus CY for any integers X and Y. This is a very important property that we're going to be using over and over. And number 8, if A divides B, then A divides any multiple of B, or any C. Some of these properties has names. For example, this property we call that this relation divides is called transitive. All right, relation divide is transitive. This A divides itself. We call this is reflexive. This relation reflexive. And divides, it's not a symmetric relation, okay? It's actually anti-symmetric, all right? So if A divides B and B divides A, almost they are equal, all right? They differ by just a sign. So if we restrict ourselves only to the natural numbers, okay, not allow negatives, this becomes actually what we call anti-symmetric, okay? This relation is anti-symmetric. All right, now these properties, reflexive, transitive, anti-symmetric, is called, it defines an order or a partial order relation on the set of natural numbers at least. All right, most of these are very, very simple to prove, okay? So just as an illustration, let me look at, first of all, I definitely want to do 7, okay? And maybe we can do, let's do also 4, and let's do also 6, okay? So let's do these to illustrate how the proof runs, actually, all right? So all of this are okay, so let's just start with 4. So we are given that A divides B implies that B is equal A R for some R in Z, and B divides C implies that C is equal AS, again for some S in Z. Now we're going to sort of find a relationship, an equation between A and C. So from here we have C is equal AS, BS here. BS. And now I want to substitute for B by AR. So this becomes ARS. Now we have C is a multiple, okay, of A. And this exactly means that A divides C. All right. So very, very straightforward. Okay, let's look at number 6. So number 6 we have A divides B, and we have B does not equal to 0. All right. Then from here we have B is equal AC for some C in Z. Well, let's look at the absolute value of B. absolute value. We could take this. Now I know that C, this is actually bigger than or equal to, let me see if this one is stated. Right. So we know that from here, since B does not equal to 0, I cannot have the absolute value of A, or actually from here even. From here, we know that A does not equal to 0 and C does not equal to 0. Because either one of these zeros is going to give me B equal to 0. So it makes then the C here, or absolute value of C, is going to be bigger than or equal to 1. All right? So this is bigger than or equal absolute value of A multiplied by 1. In other words, I'm replacing the absolute value of C by the smallest it can be. Okay? It's not a zero number, it's an integer, we have that. And this actually proves that the absolute value of B is bigger than or equal to the absolute value of that. And the last one, as I said, this is very well used property. And it says there that if A divides B and A divides another integer, then it divides any integral combination of these. That's what we call an expression like this. And again, let's go with the proof of 7. So we have A divides B. Actually, we need to actually property 8, it should come before this, okay? Because we have this from 8, this means that, actually we're going to go also from scratch here. So this one is A, C, all right, and I have to use a different one. We put R here, all right, for some R and Z. And A divides C implies C is equal to S for some S in Z. I want to multiply each of these by an X and a Y. First one by X and the second equation by Y. So I'm going to multiply, this is by X, and this is by Y. So this would give XB equal A XR, and we have YC is equal A YS. All right? And now I can add these two equations together. And this is equal a common factor, XR plus YS. So we are expressing this as a multiple of A, and this means that A divides the XB plus YC. For any C, all right, for any, X and Y. All right. We move on in here, see what else we look about this. Of course, there are a couple of generalizations for some of the properties in here. One of them is transitive, and this also linear combination. So if we have A divides BI for I equal 1 to up to n, then A divides any combination Bn xn for any integers it's very straightforward. And you can, if you want to use induction, just use a constructive proof. Another property is if A divides B1 and B1 divides, actually let me start with all A's in here. Okay, so we have A1 divides A2 and A2 divides A3 and so on, and AN minus 1 divides AN. Okay, then we can say that A1 divides AN. All right, so the transitive property goes as many of these as possible. But as far as A1, A2, this one is A2, A3, then A3, A4, and so on. All right, so this is for every n bigger than or equal to, these we need here 2. All right, so that this picture gives you a 1 divides A2. All right. I'm going to stop right here, actually, and next time I will be actually, this take care of actually section 2.2. I put actually the objectives for 2 sections, and I thought I could cover 2 sections, but probably I will leave this till other time.